Hello and welcome to another video. In this one, we're going to be talking about how I collected mypy stats from the Sentry codebase, or the public Sentry codebase, over time and generated some graphs. If you missed the Anthony Writes Code movie, where I talked about this previously, you can search for it on YouTube and I don't know, watch it maybe. But here's one of the graphs that I showed in the video. I'm going to go over the design of how I built this system to essentially run mypy 18,000 times and collect all the data together and then format it and then make it something that people could generate graphs for. And then I'm going to go through all of the graphs that my viewers made and show some of the ones that I think are pretty cool. And yeah, just walk through all of those. And if you want to look at the code, it'll probably end up being Ace archive by the time this video goes up, because I'm not going to maintain this repo. It was basically write once code, and wanted to at least put it out there. If you want to make your own graphs, I've also uploaded the data in a tag v000 called we have data, here it is, inside this TGZ. And ooh, actually, this is a nice new feature on GitHub. They've put the checksums here. Ooh, props to GitHub for doing that. I like that. But anyway, I'm going to clone this repo and I'm going to walk you through the code and kind of draw some design diagrams and how I thought about this and how I wanted to be able to use all of the CPUs in my house to work on this problem. Or at least all of the ones that were Intel that had Linux machines available. GitHub Ace/Sentry mypy stats, and this clone will still work even when I move the repo because of the way things work. Okay, so I have basically 3 scripts here. This is the easiest one to explain. This takes a SQLite database and outputs several CSV files. These are the ones that you'll see in the data TGZ, and it's just, you know, this is the last step. I'm showing it first because it's the simplest. Also, I didn't know about this in SQLite, so this is actually kind of a cool learning for me. You can change the output mode and tell it to output to files, and so this is a little script that you can run. I guess shell script is the easiest way to do this, but yeah, so this was the last step after I'd done all the processing. We'll get to the processing. Actually, you know what? We'll do this backwards because, no, we'll do it forward. Okay, so I wanted this to be something that I could run pretty portably on any sort of system. And in my mind, the easiest way to make something portable is to run it in Docker. This allows me to not really care about like what the host operating system user space is. Like, I just need a Linux kernel, I can run Docker, I can pick the particular Docker image that I'm using and make everything consistent. It also meant that I didn't have to really worry about making sure the system was in exactly the right state for all of the code to work. I could just, you know, fire and forget. And as long as I have a Linux kernel and a Docker daemon or Podman or other containerization and yeah, and this little bit of code, I can make things work. This is, where do I even start? I guess we can start with the script that I ran in Docker. So I basically started a Docker container. You can kind of see that here. Actually, I used Podman because I have Podman on my machine, and that was easiest to use on other machines, which I'll talk about later. I actually abused some free compute. I don't know, abused, like the GitHub terms of service seems to allow what I was doing here, because I was using, I'll spoil it. I use GitHub Actions for some of this because it's essentially free compute. But I think it's within the lines of what GitHub would allow and even encourage. Like there's always, like, on election night, someone sets up a scraper using GitHub Actions that generates graphs and stuff. And this is, you know, pretty similar to that, although a lot more technical, I think. But anyway, Podman command, idle cache, because that sped things up a lot. I had a vendor directory. This is where I installed a bunch of things that I was going to reuse over and over. I had the source code. I did need to check out the Sentry source code to work on this. And then a data directory. This is where I output the results. And essentially all that I was trying to do in Podman is install the dependencies, run mypy, and save the output. So I was just trying to get complete raw output of running mypy against the code base. I also collected some other data inside here, which we'll get to later. Oh yeah, this information, the Python version, the mypy version, what author made the commit, and the time of the commit. This is what I thought might be useful later. I didn't end up actually using the Python version, although some of my viewers made cool graphs that showed the Python version and some of the interesting bits there. I also recorded the mypy version. Often when changing the mypy version, this either bumped up the number of errors or reduced them drastically. Usually it was up, not down, but you win some, you lose some. But this was all of the information. So the raw mypy output and this little bit of metadata, and I tried to record it per commit inside the data directory. So, and I tried to make everything idempotent and atomic, so that's why I'm making a temporary directory and then moving it into place at the end. That way, if this was interrupted, I could restart it. That was another part of this process that I knew that I needed to do from the beginning, is I needed to make sure that I could restart this process, not have to reprocess all the data that I needed to run, and let it just skip all those commits and continue chugging along where it picked up. When I originally did this, I wrote it as a single process. You know, the principle that I usually use is 1, make it work, 2, make it fast, and 3, well, I usually do make it readable, then make it work, then make it fast, or you know, make it work and readable. I usually do those at the same time. But then optimize it and make it fast is kind of the last step. And so the first thing that I targeted with this was just get a single core running with a single Docker container. You know, no fancy multi-processing or any of that stuff, just like one at a time, and see how long that was going to take. And I think my initial estimate for this was that it was going to take like 30 days to compute all of this data, because essentially it's, you know, 18,000 commits, and it takes, the older commits, it only took like three or 4 minutes to run. On some of the middle commits, it took like 5 or 6 minutes when mypy was a little bit slower. By the end, it was back down to like 2 or 3 minutes as well. But, you know, 18,000 commits times 2 or 3 minutes is quite a lot of time. And that was on my main machine, which is faster than all the other computers in my house. So, yeah, basically that's the you know, design that I took here. So run Podman. Inside Podman, I ran this little script here. I utilized UV because that was what Sentry used to install dependencies. It made it ever so slightly faster than using pip. I could have just used pip with a cacher and it would have been about the same. With find links and ignore index, and actually wrote a tool at Yelp called pip faster, which essentially did that. Like it was, I didn't write it, but one of my coworkers wrote it. I worked on it a bunch, and then we killed it because it ended up, you know, it was nice, but it was a lot of work to maintain it and keep it working. But anyway, UV into the cacher and make a virtual environment using the Python version that we're targeting. If it was in the old mode, we would use UV pip version, which UV pip has some weird quirks, but we'll get to that later. Then if it was in the modern Sentry setup, it would just use UV sync, active frozen quiet cacher. This was specifically so I could cache stuff outside of Docker, so I could reuse it between runs, because I'm essentially throwing away the container every time. I vendored a copy of this script that I wrote at Sentry called fast editable. This is pip install -e dot, but it takes, you know, 4 milliseconds instead of the like 5 to 10 seconds that pip install takes. Turns out you can make the editable structure really, really quickly if you just skip the slow parts, which is everything that pip does. Sentry has weird side effects, so you have to initialize it. Fortunately, this is in a container, so I wasn't worried about it doing its weird side effects outside of the container. Record the mypy version, this way I can generate the data that I was looking for. And then run this script that's present in the repository to generate mypy without the ignore list, because there was an ignore list, so mypy was actually clean when you ran it, but this would generate the data. I also inverted the exit code because this will always, if done correctly, this will always return non-zero because there were errors, because it just forwarded the mypy error code along, and save the output. And if this crashed, which it only crashed on 3 commits, I basically just threw out that commit. So 18,000 minus 3 commits, I think we can live with a few commits failing. Those were merge races. If you're familiar with the idea of a merge race, it's basically an implicit merge conflict where 2 branches change either the same file at the same time, or something depends on some other thing, and neither of the change sets know about the other one. And it doesn't cause an actual merge conflict because they're not touching the same lines, but it results in something where the merged thing fails. And I actually talked about this in a video about merge queues. YouTube. I think if you search, let's see, merge queues. Let's talk about the level 80 cheaters. Let's not. Merge queues. So if you want to watch that video, it talks about merge races in more depth. But this is essentially the script. You know, install the dependencies, run mypy. That's essentially what I want to do, and I want to do that across everything. So let's talk about the evolution of how this design started. So initially, yeah, we got paint out again. Initially, it was just like, oops. I mean, this process sort of started the same for all of them. So the first is find all the commits to do. And this is essentially, you know, git log on all the files. And record all the commit IDs, and that's the stuff that I knew that I needed to process. Subtract out all the ones that are done. 3, start a Docker container, and then save the results. And this initially started as just like a single instance, single CPU. So this is version 1. And once I got this building block working, this like version 1 with just a single Docker container, where's my rectangle? Docker containers will be blue. This worked really great. There was no queuing, there was no multiprocessing, there was no distributed system. It was just very simple, run things serially, get a for loop working. Once you have a for loop working, you can start optimizing it further. Ooh, we don't need a little tiny Docker container right there. Once I had done this, I wanted to be able to parallelize this within the same machine. So I switched it to a queue setup, so v2. And this queue setup sort of ended up being the same thing that I would use for the rest of it. So v2, there was a queue, just an in-memory queue. It didn't need to be anything fancy. This is a queue. And then I had a series of workers inside the same machine. So this is still single machine. And each of these workers, I would pick as many as I could per core. And they, oh, nope, stay that color. Okay. New paint. New paint is different than old paint. So I would have a queue, and the workers would pull work off of the queue. And do I have arrows? No. Anyway, the workers would pull work off of the queue, and I was able to distribute the work within a single machine. And so if we look at the actual, yeah, that's what this threaded worker is here. Basically, it retrieves an item from the queue. If it's empty, it's done. It does the work, and otherwise, it's, you know, pretty simple. Just does the work. We already sort of showed this with it, you know, cloning the repo, checking it out, and figuring out the author name and time, blah blah blah, running Podman, etc. But even with the number of workers that I had here in version 2, I knew that this wasn't going to work, or this wasn't going to complete in any reasonable amount of time. This was estimated like 30 days when I had all, I don't know, I think I allocated 12 cores to my machines, or to this virtual machine, and it was still going to take, you know, well, 30 days divided by 12 minus a bunch because I didn't actually balance things properly. It was still going to take like, I don't know, 10 days or something, like 5 days or 6 days or something like that. And I didn't want to wait that long. I didn't want to keep this machine up for 10 days. So this wasn't going to work. I knew it wasn't going to finish in time. But, oh, I did want to talk about one other thing. I mentioned there that just adding 12 cores didn't actually reduce the problem by 12. And that reminds me of an interesting issue in these sort of distributed optimization problems, which is that you need to consider what resources you have and whether you can bin pack things properly. Fortunately, in this case, almost all of my work is the same exact shape. Like, I know about how much memory it's going to take, I know about how much CPU it's going to take, and I know about how much disk IO it's going to take, and I know it's not going to take any network. And those are kind of usually the four, like, I mean, there's obviously more, like you could have database throughput and other stuff like that. But when I think about distributed systems, those are kind of the four things that I try and figure out how to balance and bin pack in my systems. And so in this particular case, and actually when I thought about this problem, I didn't even think about disk IO at all. And I was quite surprised to find that that was often the limiter in this. I had a machine downstairs that had fast CPUs but terrible spinning media, and it performed extremely poorly on this. And even like, it's like, oh, it has so many cores, I can bin pack so many things on this, and everything ground to a halt. In this particular case, I knew about how much memory this would take. I think the processes took close to 2 gigs of RAM per execution. It's got to hold a lot of code in memory. It's like several million lines of Python and several thousand files, so it doesn't surprise me that it takes a lot of memory. MyPy is single core currently, and so I knew that I could, if I had 8 cores, I could roughly hammer 7 and change of them and be okay with that if I needed a free core to do other stuff. And I didn't really factor in disk IO, but it turns out that a big part of the MyPy, like the speed of running MyPy or running MyPy a bunch, is it reads everything from disk, and it does that a lot. And that was kind of the surprise here. Okay, but anyway, V2, I had this queue, and I had these on-machine setup here. V3 was a nice little extension from this model. Fortunately, I structured this queue in such a way that like I could interrupt it, I could start it over. Show that a little bit here. So we got a queue here. We figure out all the commits that we need to. This is just a determine commits. Where is the code for that? Yeah, so basically log all of the things. Git leaves out this commit for some weird reason. Find all of the data that we already have and remove that. Also delete anything that's garbage or interrupted, or if I Control-C this. So we go back to our queue. Nope. Here. Well, that search was not unique, but got me to where I needed. I set up this queue, put all the commits in it, and then started all of my workers. Spoilers, V3 added SSH and V4 added GitHub Actions. But I would start all of my workers. They all had access to this queue so they could retrieve data from it. For SSH workers, I attached a little bit of information about like what host and how many cores I could use on that host. For GitHub Actions, I also just passed along the queue because it didn't need any additional information. I used credentials to set up the GitHub worker, and then just had a bunch of threads running their queues. The SSH worker is kind of cool. I actually really like how it worked. So there was this like SSH thing here, which just had a host and number of jobs. And the cool thing about the SSH worker is it could just reuse all of this threaded queuing. So all it would do is spin up the same process on another machine. So V3 was adding, we'll do a curvy line because that looks cool. And we'll, I don't know, make it red. Curvy line, yeah. And then a box for V3. So we'll just call this V3 SSH. And it basically just replicated this same structure on a separate machine. And so I could use all of my terrible laptops that have been sitting on a shelf for years, and even though they're, 2012 or 2014 CPUs, they're still CPUs, and so they were still able to, pick up work from the queue and, meaningfully improve the amount of end-to-end time it would take to compute and crush all this data. And so we have this little parsing thing, and then the SSH worker is essentially SSH to the host delete any in progress data, and then run what? Oh, run another SSH command, which reruns the thing with the number of jobs that it specified. And you could also specify the specific commit IDs on the command line, so I could reuse the threaded worker. And then SCP the data back. And it's, you know, as simple as that. I was able to basically take my core building block, replicate it on another machine, and use some, you know, bad CPUs to do some data here. Now V4 was adding GitHub workers as well. This is the part that I'm, you know, not as don't feel as great about, but it did what I needed to do. Where's the selection tool? Is this a selection tool? No, it's this one. They keep changing it. We're gonna get a little red bit here, but V4 actually looks the same as the V3. Can we curve the line so it doesn't look? Look at that, nice. So V4 was GitHub Actions. So take the same process, but instead spin up I had a GitHub token. I would still pull queue items in the same way. I pulled them in chunks of 16, which seemed to line up nicely with the number of cores on the GitHub Actions worker. Just API request to trigger a workflow, wait for a while, because if you pull, I found that if you pull, you're kind of just wasting time in API requests, and also the API requests were kind of flaky, so had to do some funky, janky retries here. But it was essentially just run the GitHub action, wait for the artifact at the end, unzip it, and copy it into the output, and then delete the artifact at the end. And just use a simple GitHub action. This is the same thing as before. Clone the repo, run the script, upload the artifact. Very simple. Basically reusing that same building block and building a cool distributed system. So all of these things, all of these, you know, SSH workers, the GitHub action workers, and the threaded workers all pull from this queue. The other thing that I really like about this, which is not related to the design, but just something that made this easy to, you know, start over or you know, rework with it, is I made a way to stop the queue gracefully. I couldn't figure out how to do this with Control-C, and I spent a bunch of time mucking with Control-C as a signal handler, but eventually gave up. There's some weird threading thing that I know I've fixed it before, but I couldn't find the code for it because I'm pretty sure I lost it to closed source. But there's some like signal handling thing you can do in threads to make Control-C work reasonable. But I just changed to SIG-user1 instead, and all it did here is retrieve the items from the queue and just discard them. And that way, any of the workers, if they ever try to get an item but don't get one, they can just exit immediately. Also, I think I learned later that I don't actually need timeout here. Yeah. No? Yeah, I should have just used this instead. But write once code, and I didn't really think about it, so I didn't go back and fix it because it worked. It was good enough. But this was kind of a cool little gadget to make it so I could interrupt the process and start it over. For instance, if I needed to add or remove hosts, or like my internet went down, or like all sorts of stuff, or if things failed, because you'll notice that I have 0 failure checking here, which is fine for this thing. It was good enough and got the job done, and I wasn't gonna spend a bunch of time making these things resilient. It wouldn't have been too hard to make them resilient, you know, basically just retries on some of this stuff. Like I did make this retry because it was really flaky, but I could have, you know, optimized for SSH, or like if this host went missing or other stuff like that. I just didn't bother, because why bother? Okay, anyway, that's kind of the design of that. After we had the raw mypy output, I basically, 4 commits that failed. I basically processed it with some regular expressions and wrote out the various data, but I used SQLite here because it felt like a good fit to store this stuff in tables. Also, it made it so I could query it if I wanted to. I ended up not querying it in the SQLite database, but I thought it might be useful, but it ended up not really being useful, so whatever. CSVs were easier for the data sciencey people to do the data sciencey things that they wanted to anyway. But yeah, basically go over all of the error files and slam them into the database. And once we're in the database, that that shell script that we saw before, converted them to CSV, and I upload that artifact. Okay, so that's the design of this thing. I want to go over some of the graphs that my viewers made. And so this is kind of the first one. Oh, I just realized that I need to move one of the graphs into the right directory because it is here, but I need it to be in my VM so I can actually open it. I guess I could open it here. Yeah, we can open it here. Maybe. Yeah, okay. Sort of. Oh my goodness. Opening this, it's a 21 megabyte HTML file because it's just vendor libraries in the middle of it. Yeah, we're gonna do this in no particular order. Actually, we're gonna start with all of the ones from the endless server. And I don't have real pros from these. I'm just gonna talk through them and look at the things that I think are interesting. And we're gonna shrink this down so that I can actually make it render properly. Oh no, what have I done? Go here, yeah. Shrink this here, make it fit. That's probably, no, don't do that, Windows. It really wants to stretch this. Okay. All right, so this is a graph of the mypy errors over time, but with the Python version also annotated here. You'll notice here that there's a very quick jump from 3.8 all the way to 3.11 with a little, you can see a little bit of 3.10 in here. I talked about this in the video, but I optimized the process for upgrading Python, and so it's very easy to go from version to version. Very easy, I say, but you'll notice the orange and blue or orange and green lines overlap a lot here, going from 3.11 to 3.12. This was a really difficult rollout due to some other stuff, but I also have a video on that, so you can check that out as well. But you can see here like 3.12 to 3.13, trivial, like one commit. I think I almost first tried this one. But you can kind of see the progression of this line over time with Python versions. Okay, we got to go faster if we're going to ever get through this. This one, I think the graph is inaccurate or scaled in some weird way or smoothed in some weird way. But I think this got corrected in the HTML file we're going to look at in a bit. But this was supposed to be a like proportion of error codes over time. However, I know it's not correct because, for instance, this, no, not that one. Which one is it? Call arg green. This one only had like 2 errors at the end of the 240, so the proportion I know is not correct here. But a cool graph nonetheless, and we'll see a corrected version of this soon. This is a theme that we'll see in a lot of the graphs. Top 20 authors reducing mypy errors. Spoilers, it's me. This one's also, I mean, not to call people out, but like, there were also people that pushed things in the other direction. One thing that I would do if I went back and reran this data again, which I don't really want to do. Actually, I could probably just rerun it for the ones that are committed by Git sentry bot. These are almost always reverts of my commit. And so attributing these to the bot is maybe not correct. When fast reverts were made, they're made by the Git sentry bot. With the co-authored by of the person who clicked the button, but it probably should. My script could have done better and attributed that to the original author that was getting reverted. That way, it would net out to 0 and not attribute reverts to bots. But yeah, okay. And then the rest of them are in the thread. So let me get the thread over here. Is this the thread? Yes. Okay, but I'm also going to do that. This one from the endless server. This is the interactive version of those same graphs. I should have just shown this. This is better. This one I think is really cool. It's kind of this is the proportion graph, but actually scaled properly. And so you can see portions on the graph where either like I made a big effort to reduce a particular error code, or like I think, can you click into these? Oh, you can. You can undo and show them. Wow. Okay, this is really cool. But you can see like where I, put an effort in here to get rid of the index code. And so this one dropped to 0. Whereas almost all, I think this is a log scale as well. So MISC, the hardest error code to fix. But adder to defined, and I want the orange one. What's the orange one? I don't know, whatever the orange one is. We're probably union adder if I had to guess. I don't know why I can't highlight it, but it's fine. But yeah, I guess these are just the same graphs as before, but in like an interactive version. Oh, this one's cool. Can I zoom in? Oh, I can. Oh man, that's so cool. Wait. Oh, double click to zoom back out. Yeah, so if we ignore like the first part of the graph, you can kind of see like a more, man, this is cool. And you can download this HTML from the Discord if you want to poke around with it too. Errors are moved by day of the week. So I think this was normalized to local time and probably should have been localized to either Eastern time or Pacific time. But I think this also makes sense to me. I was almost always trying to merge earlier in the week and not later in the week, although sometimes I just didn't care and would do it on Friday. Cool graphs. Okay, let's go into the thread now. And yes, the data, of course. So this first one is from Pandoxer. This is kind of a cool just terminal view of the progression of errors over time. They chose max errors as a good representative for the month. And you can kind of see a cool terminal graph. I thought this one was really nice because it shows nicely in the terminal. They also found the biggest fixes and offenders and linked the commits, which I think is kind of fun. The worst one, spoilers, it's me. I'll talk about why in a bit. But this was actually the biggest reducer, which is all these files got fixed, and it was essentially this one-line fix here. I think I talked about this in the video. I don't remember, but name aliasing problem that mypy turned into 8,000 errors. But this one actually increased the number of type errors, and this was a compromise because each of these links is a dependent task that I needed to fix mypy errors in order to get this working. This was the first time that we enabled the manager typing in Django models, which Sentry has a custom manager for reasons. You can debate whether they're good or bad. But basically, I wanted to enable that so that we could get proper type hinting and checking for manager stuff. And that involved fixing a lot of stuff because there were a lot of things that were just broken and doing all that. But I didn't bother fixing the stuff in ignored files. That was kind of my trade-off here, in that like I knew there were lurking errors in files that were ignored, but fixing them was going to be, you know, another 100 of these PRs that I just, you know, decided this was so much better than before that it was okay increasing the number of errors. So that's why I plus 108'd there. What's this one though? Oh, yeah, I remember this. This was before I fixed the strong list. So something got added to the strong list that was also in the ignore list. And so it looked like everything was strongly typed, but it was actually just increasing the number of errors. Okay, anyway, onwards. Bingham has a nice little chart here. This is similar to the one before with number of errors fixed by people. And again, get sentrybot, what are you doing? Here's some errors over time. We'll see the same graph a few times. This is number of files with errors over time. The graph is actually pretty similar in shape. But the number of files with errors is kind of the unit of work that the block list worked on, and so it sort of makes sense that this would happen. Although sometimes I would just fix files or fix errors in not the whole file. I would, you know, do it by code instead. Unique mypy error codes. You can see this is where I put an effort in to actually. I think I introduced the ability to ratchet by error code here, and so put some effort to kill some low-hanging fruit here, and a few right at the end as well. But cool graphs. Bingham also split some of them by the various directories, so you can see like most of the giant reduction was in the test directory, which makes sense. There was also, I guess, some in source, but you can see like kind of the reduction over time. The nice thing about errors in tests was it was a lot safer to fix them because you knew they weren't going to break production. And so that's why, you know, easiest things first, tackle the tests. This number actually didn't go to 0 because there was a few tests that did some things that were so horrible and difficult to fix, like 6-level mix-in inheritance that just like... It's like, I'll tackle that later. All right, particularly Pythonics graphs. This is actually the one that we showed before, where you can see the error, the coloring for increase and decrease or staying the same. Same graph of by user as well. Reduction ratio, I'm not sure what that means. Top 50 commits by error reduction rate. So you can see a lot of them are in the small number, but obviously there's the two big ones that happened here. And a lot of red dots because, yeah, it's me. This is net impact of error reduction, but in a circle graph. I think this graph is kind of hard to see the other circle sizes, but it's cool though. I like it. And I guess this is a long plot of every author that increased or decreased. Fortunately, I mean, you can't really see it here, but the ones above this plus are all decrease. Or zero? Or zero. I should have cut out the zeros. Maybe some of them are plus and minus, and so they net it out, but most of them are non-negative, which is good. And they included their code, which is also cool. Bingham says here, if you place in the code base that saw biggest reduction in errors. Okay, yeah. So splitting it again by directory to see more specifically things that got reduced, which is pretty cool. And then we saw the HTML plot, and we already saw that one. And that's the graphs that my users made. And the data is available on GitHub, so if you want to make some as well, feel free. Where did my Chrome window go? This one. Cool. Yeah, so there's the data there. And that's that. This has been, a really long video. Oh, whoops. Anyway, hopefully you found this interesting. If there are additional things you'd like me to explain, leave a comment below or reach out to me on the various platforms. But thank you all for watching, and I will see you in the next one.